Hi everyone, thank you for tuning in to another video to learn about features in FHI-aims, an ab initio material simulation package for materials science and chemistry. Today I want to talk about calculating diffusion barriers in solid electrolytes with FHI-aims and aims chain. The results I will show you today are published here by Banerjee and Chachenko. A written step-by-step tutorial to obtain these results is also linked in the description. Let's dive right in. Energy storage is an important building block for a sustainable future. While lithium-ion batteries have revolutionized portable electronics since the introduction in 1991, solid-state batteries represent the next leap forward, offering potential advantages in both safety and energy density over conventional liquid electrolyte batteries. At the heart of these batteries is the solid electrolyte, where lithium ions need to move efficiently between electrodes. Understanding exactly how these ions move through the crystal structure is crucial for developing better batteries. This ionic transport determines both the power capability and rate performance of the battery. Today, we'll look at how to find transition states using FHI-aims in aims chain in one such material: lithium, phosphorus, sulfur iodide, which I will call LiPSI for short. This material belongs to the ajaradite family of solid electrolytes known for their high ionic conductivity. And here we have the crystal structure of LiPSI. The purple tetrahedra you see are phosphorus sulfide units with iodine atoms in purple and sulfur atoms in yellow. The mobile lithium ions are shown as small green spheres, and what we want to understand is how these lithium ions move through the structure. Specifically, we will look at one particular hop where lithium ion jumps between two sides separated by about 3.3 angstroms. Understanding the energy for this process tells us how easily lithium can move through this material. Now here's the challenge. We need to find not just the starting and end points of this jump, but also the optimal path between them. And this is where transition state searching comes into play. To find this transition path, we'll use FHI-aims and aims chain, a tool that helps finding minimum energy pathways between two given atomic configurations and which is closely integrated with FHI-aims. Let's look at what we found here. This energy profile shows the optimized diffusion pathway for that lithium hop I just mentioned earlier, and here the x-axis represents the reaction coordinate, essentially how far along the path we are, while the y-axis shows the relative energy. The maximum point on this curve, roughly 0.4 eV, represents the energy barrier. And this already agrees quite well with experimental measurements of around 0.39 eV at room temperature. Interestingly, if we compare this optimized path to a simple linear interpolation between the start and final positions, we see a dramatic difference. The linear path here would predict a barrier of over 1.5 eV, nearly 4 times higher than the optimized one. This highlights why proper transition state searching is crucial. Interestingly, different computational methods can also give varying results. When we compare here, for example, the PBE solve functional with a more sophisticated hybrid functional like HSEO6, we see some interesting trends. The highest barrier, which is around 0.45 eV, comes from the hybrid functional HSEO6 combined with the non-local many-body dispersion correction. And this matches experimental measurements best. The question is, why? The answer here lies in how this method captures the subtle electronic effects during the lithium migration. As the lithium ion moves through the crystal structure, it creates a complex electronic disturbance within its surroundings, something simpler methods might miss. Interestingly, when we use a simple pairwise van der Waals correction, here the Chachenko-Scheffler method, TS, we actually underestimate the transition barrier drastically. This happens because the method overestimates the stabilizing interactions at the transition state. The many-body approach, in contrast, provides a more balanced description throughout the entire transition pathway. So to conclude, while simpler methods can give us qualitative insights, capturing the subtle effects often requires more sophisticated approaches. For solid-state battery materials like LIBC, accurately predicting ion mobility means accounting for both the atomic scale structure and the electronic response of the surrounding framework. And with this, we are at the end of the tutorial. Thank you very much for tuning in. Please check out our website and online tutorials for more examples. Happy simulating!